everyone. As Sophia said, my name is Kathleen. I'm a research engineer at Google DeepMind and one of the founders and technical leads of the Gemma team. I'm so excited to be here with you all today. When we were building Gemma, our North Star and the thing we were most excited about was building a tool that would accelerate the great work being done in the open source community. It's been almost exactly a year since we first launched, and I've been absolutely blown away by the incredible research and projects and innovations that people have built using Gemma. So I'm particularly excited to be here with you all, with so many developers and engineers and scientists today. So without further ado, here's a little bit of how we developed Gemma. And to start, I want to place our development process in context. As many of you probably know, Google has been a pioneer in publishing AI and ML research for the past decade, including publishing a lot of the work that has sparked the new wave of innovations that we're seeing today. Work like seek-to-seek models, the transformer, BERT, and many more, including a lot of work across the entire technical stack, from hardware breakthroughs like a TPU to an evolution in ML frameworks from TensorFlow to JAX. And throughout this entire history, open development has been incredibly critical in allowing us to innovate faster, collaborate closer with our external colleagues, and to push the limits of what we believe is possible with AI. This long history brings us to today, and in particular, to the Gemini era. Gemini is Google's state-of-the-art frontier model. It's multimodal, it reasons, it thinks, it's capable of really incredible creation. And especially over the last couple of months, we've seen every new iteration of Gemini hit #1 on the LMSys leaderboards. We're really excited about the progress we're making there. But we also know that the raw power of our frontier models is not enough to fuel the next wave of innovation, and that true change comes from putting that power in the hands of all developers. And that's where our latest investment in open source comes in. Gemma is built on the same cutting-edge research and technology as Gemini. It's a family of lightweight, open models meticulously crafted for you. Our goal with Gemma is to put the power of our frontier models in the hands of developers to accelerate your work. Our latest release of our foundational models is Gemma 2, which comes in 3 different sizes: a 2 billion parameter model, a 9 billion parameter model, and a 27 billion parameter model. And each one was designed with a very specific purpose in mind. The 27 billion parameter model is our powerhouse model. Upon launch, it stormed the LMSys leaderboard and was the #1 open model, which means that it outperformed models 2 to 10 times larger. But what I'm particularly proud of is the performance that we've achieved with our smallest models. Our 2 billion parameter model handily outperforms GPT 3.5 on LMSys, which is sort of crazy because we know GPT 3.5 is many, many times larger. So this means that we have the power of GPT 3.5 in your hands. You can run it locally, on device, you can fine-tune it, you can use it to build whatever you want. If you're looking for a balance between the power of our 27B model and the efficiency of our 2B, we also offer a 9B parameter model, which has been incredibly popular and performative. The most important part of that is that this performance is available to everyone. At the heart of Gemma is a commitment to building tools that are actually helpful and useful for you. We know that models gated behind an API aren't useful in every development case. You might need to run a model locally, and there might be legal restrictions. You might want to fine-tune in ways that are just difficult with a model behind an API. We've designed these models to really empower those additional use cases. And most importantly, you don't need crazy hardware to run these models. You can run them on your phone, on your computer, on a single GPU or TPU. And it's easy to harness the power of Gemma. Importantly, we refuse to sacrifice quality. We make small models that you can use anywhere, but we want to make them state-of-the-art and as powerful as we possibly can. That's our goal. And it's also our biggest challenge in developing the Gemma models. As many of you probably know, if you've tried to train models, the best way to improve performance is to scale up your model and add many, many more parameters, and it's really easy to see increased performance. And that's the opposite of what we want to do for Gemma. We're constrained to small sizes because we want to meet developers where they are. So when we're developing Gemma, we're caught in this tension between having small models and trying to compress as much world knowledge and skills and capabilities as we possibly can. So that's our goal when we develop Gemma. From here, I'll dive into exactly how it is that we try to pack these small models with so many state-of-the-art capabilities. Our development process is split between two different phases of training, pre-training and post-training. The goal of pre-training is to compress all of the world's knowledge into our model weights. We're trying to encode all sets of possible responses to an input, all the possible generations and knowledge that you could see, and squeeze it all into our weights. Once we have all of that knowledge encapsulated, the goal of post-training is to help the model choose its behavior. So if you have an input and you've encoded all the possible responses that you could say to that input, the goal of post-training is to help you narrow down actually how you would want the model to behave. And this is the part of the process where you can actually really build a useful model for product. You can build a model that's good at chat, or question answering, or summarization, or analysis, or all of the above. This is an overview of the pre-training life cycle of Gemma. And importantly, it really is a life cycle. There's 4 stages that we iterate through, and then we repeat this process many times over to develop better and better pre-training recipes. The first step of this process is dataset selection. We trained the Gemma 2 models on up to 13 trillion tokens of text, mostly web data. We used a combination of both English and multilingual data. We also added a large amount of mathematical and STEM content, as we find that that really improves logic and reasoning capabilities. And we also add a lot of code. We're also always looking to select data sets for new domains, which is an ongoing research area and challenge, and an area where, in particular, we'd like to collaborate more with the open source community to find areas where the Gemma models are currently bad, and we could add more data and target better improvements in these domains. Once we have a bunch of dataset sources, we sample from each of these sources to create a mixture. And from there, we try to improve the quality of our mixture. We start by first doing compliance filtering. When you work with an open source model that's not behind an API, we can't use any sort of safety filters. We can't protect or prevent harmful outputs. So our goal in building a safe model is to try to make sure that the model doesn't see harmful data from the get-go, so that it has a harder time learning to generate a harmful output. So when we say we do compliance filtering, really what that means is we're trying to remove a couple of specific categories of harm from our data. We want to remove any personal or sensitive information. We want to have, a very private model. And we also remove CSAM data, as well as a couple of other sort of violent or offensive categories of data. Once we've done compliance filtering, we do a lot of analysis to make sure that our dataset mixture looks as safe as it possibly can, that it doesn't contain a lot of harmful output. And then we do quality filtering. So our goal in the dataset mixture is to make sure we have incredibly high quality data. We want to make sure we have correct understanding of grammar and that our model can speak eloquently. And that primarily comes from seeing great examples of writing. We do a lot to make sure we remove spam. Nobody wants a model that adds more spam to the world. We certainly don't. We work a lot on trying to improve the formatting of our data because we love to see great grammar. And we also work to reduce duplication. This helps us make sure that we're not wasting training space looking at the same data over and over again, and that we can see as broad a set of text as we possibly can. So our goal in our quality filtering is to prioritize allocating tokens to unique and high quality content to improve both the breadth and the depth of the model's knowledge. Once we have a really safe, really clean dataset candidate, we run some ablation studies, which is basically like our small scale training runs where we evaluate how good a proposed mixture is. And when I say small scale, we're talking about like potentially as small as 100 million parameter models up to about 1 billion parameter models. So we operate at a smaller scale so we can iterate quickly and see results almost immediately. We look at a bunch of evals, including perplexity and training loss, as well as standard benchmarks like MMLU or ARC, and evaluate how our dataset mixture has impacted our model. If our evals don't look great, then we start this whole process over again. And in particular, we do a lot of analysis about which specific capabilities are missing. Where are we, which domains are we really failing to deliver good performance? And we might, if we see really bad code performance, we might add more code data to our mixture and do this entire process again. Once we have run ablations and we feel really confident about the performance of our small models, we start training our larger models. There's a lot we could dive into about the training methodologies that we used, but I want to highlight the one major breakthrough that is the primary driver for our great Gemma 2 performance, and that's knowledge distillation. If you're not familiar with knowledge distillation, I like to think of knowledge distillation as like doing next token prediction with the best tutor you could possibly find. So we do like standard next token prediction. We have an input, we're trying to predict the next word. And while we're training our small model, we also run a larger, better teacher model. And as our small model is trying to guess the next word, we also have the better teacher model tell us what they think the next word should be. And this helps our small model guess better and more efficiently, and we can use our training steps more efficiently. It's sort of like if you were taking the SAT and doing practice test after practice test and couldn't figure out why you were getting questions wrong. It would be really great to have a tutor come in and help guide you and learn more effectively and efficiently. We found knowledge distillation to be such an incredible improvement in performance that we proposed renaming the Gemma 2 paper to be knowledge distillation is all you need, which I say somewhat jokingly, but in all seriousness, knowledge distillation is the reason that we see incredible performance for the Gemma 2 pre-training checkpoints. It is the reason that we're able to outperform models 2 to 10 times as large as our models. We are a little bit limited on time, so I'm not going to go too much further into knowledge distillation, but I would really encourage you to check out the Gemma 2 paper because we outline all of the ablations that we ran, our sort of sneak preview of some of the experiments that we saw. In one of our ablation studies, we trained a 2 billion parameter model both from scratch and distilled from an only slightly better 7 billion parameter model, and saw an almost 8-point jump in performance across standard benchmarks. More importantly, we saw that those performance improvements scaled. So we trained a couple of small models that you can see here, and this table outlines the training perplexity on a held out eval set. And you can see that our perplexity goes down at every scale. So we're able to learn our data set more efficiently across a wide variety of scales, which is great because it means that we can apply this methodology not only to the smallest Gemma models, but also to the largest Gemma models. We have yet to see a scale where knowledge distillation is not incredibly helpful. Maybe someday we'll reach its limits, but so far we haven't gotten there today. There are a couple of challenges I want to highlight for pre-training. One of the primary ones is that our evals right now are incredibly limited. We have a lot of standards like MMLU and ARC. We know that there's a lot of, across the entire industry, people struggle with eval data sets being leaked into pre-training data. This is something we're super cautious about and filter for very aggressively. But we also know that these are really noisy signals. So when we're doing these ablation studies and trying to iterate on our training recipe, and we don't have great evals to look to, we have noisy signals, that makes our iteration more difficult. Better, less noisy evals is an open area of research that we're really excited about. Scaling is another area of research we're particularly excited about. There's a lot that we can learn starting with small models and scaling up to bigger models. And in the case of something like knowledge distillation, we had really clean evidence to suggest that scaling that method up would work well. But that is definitely more of a rarity. It's often very difficult to create great scaling laws. And so we're really excited about better, more consistent scaling law development. Finally, as I mentioned previously, new dataset curation is really hard. We were just talking before this lecture started about curating datasets for new indigenous languages and how difficult that can be, and is an area where we would love to see improved performance. So we're really excited about curating new data sets and hoping to collaborate a lot more with the open source community to help us identify some areas for future work. That's the high-level overview of pre-training. So to summarize, when we end pre-training, we've done all of our data set curation, we have a safe, high-quality data set, we've iterated in our training methodology, and that leaves us with a very small, very highly capable model that knows a ton about the world's knowledge and doesn't really know how to say it in ways that are helpful or useful or chatty or any other quality you might look for in a model. And that's where we begin post-training. Our goal is to select the model behavior that will actually be useful for users and developers. This is a slightly different process. It's a three-stage process that notably is not a life cycle. This is not a process that we iterate on and the final stage helps inform our earlier stages, but rather we run this process sequentially, iterating in each phase and then building better and better models as we go through this process. So our process specifically involves 3 stages: supervised fine-tuning, or SFT, RLHF, reinforcement learning from human feedback, and model merging. And throughout this process, the Gemma team at least is optimizing for helpfulness while trying to minimize any model harms related to safety or hallucinations. There's lots of things you could optimize for in this process. You could optimize for having a model that's great at dialogue or a really great coding assistant. And because Gemma is a foundational model, we really want to make it as broadly useful as we possibly can and not make it too specific so that it's not actually helpful for the use cases you may need it for. So we're very general in that we optimize for helpfulness and trying to reduce risk and harms. The first stage of this process is supervised fine-tuning. And in this process, we run behavioral cloning on both synthetic and real prompts. Of course, fine-tuning requires a prompt and a gold standard output that can help coach our model in how to behave. Getting that gold standard output can be very difficult and expensive. So we create our output set by querying a larger, better teacher model. So we also have synthetically generated responses to our prompts. We use these real and synthetic prompts and responses, and then also apply knowledge distillation with a better teacher in the fine-tuning process. I'm going to assume many of you are probably familiar with the RLHF process. If you're not, at a high level, RLHF is a process where we train a reward model to be aligned with human preferences, and then use that reward model to score our model's outputs and tell us whether or not we're generating high quality or low quality responses. If you're not super familiar with this process, again, would recommend checking out the Gemma 2 paper and some of the great works that we cite there. But right now, I'm going to highlight, instead of like sort of our general RLHF process, 2 innovations that I'm particularly excited about that were key drivers for Gemma 2's performance. And those innovations are the bond algorithm and the warm algorithm. Bond, thank you. Bond stands for best of N distillation, which is a strong but expensive inference time method to improve model quality. So instead of sampling one output for the model and scoring that, you can instead sample N outputs, score those outputs to identify the best, most high quality response, and then serve that most high quality response to the user. We can formulate this sampling as a distribution matching problem and then teach our models to prefer these higher quality outputs, again, leveraging knowledge distillation. We also combine bond with warm, which is weight averaged reward models. This technique is also fairly straightforward. Instead of having a single reward model that we use to score our outputs, we train a couple of different reward models. And in particular, we can develop different reward models to be great at different domains. So we can have a code expert reward model, we can have a multilingual expert question answering and summarization, and we can have each of these reward models score our outputs and then average those scores together so that we can get diversity of responses and really positively score models that are great in one domain, even if they're not necessarily great in another. We want models that can produce great code outputs, even if a multilingual reward model would say that that wasn't helpful. So this allows us to really increase performance across a variety of domains. I would recommend that you check out the Gemma 2 paper for more details on this, as well as both Bond and Warm recently had papers published with all of the details about the effectiveness of these methods. The final step is that we do model merging. So our first two steps, SFT and RLHF, we run several times with different hyperparameters to generate a couple of different candidate models. And at the very end of this process, we average all of these model weights together to create one single model candidate. And we've found that across the board, this sort of model merging allows us to produce a couple of different candidates that might have different strengths, and then to put all of those strengths together into a single model. And this combination of methodologies has been incredibly effective. This is comparing our Gemma 1 models to the Gemma 2 models, where we actually see the Gemma 2 billion parameter model pretty significantly outperform the Gemma 1 7B model. And then that performance just continues to scale with both the 9B and 27B models. I'm about out of time and want to save as much time as possible for questions, but I would be remiss if I talked about the development of Gemma and didn't talk about the key final stage, which is actually releasing those models out to the world. There's lots of arguments for why it's great to have state-of-the-art models behind closed APIs, but the Gemma team and Google see incredible value in actually making the model weights themselves publicly available. It helps us democratize innovation. It puts the power of our state-of-the-art technology into the hands of developers so that everyone can help us determine what the next wave of innovation should look like. It also just helps us accelerate research. By making our tools publicly available, it allows us to collaborate much more closely with other labs, with academia, with other developers, and together we can fuel a new cycle of research. We also believe that having transparently sharing model weights just makes AI more trustworthy and safer for everyone involved. Having open weights means we can do deeper analysis about what's actually happening within our models and pinpoint areas where we're not doing well and can be doing better. We also know that an API just doesn't work for all development use cases. So having open weights allows us to meet developers where they are and make sure we're serving as many development use cases as we can. And finally, our greatest hope for the demo models is that it means we can all shape the future of AI together, that we can leverage the TPUs and training power that Google has and give that power back out to the external community so that we can all have a voice in what AI should be. So I'm particularly excited to hear from you guys about what you're working on and what you want to build with Gemma and what we can do to build better models. Thanks so much.